Hello, my name is Ernesto Pineda and I am a math physics student at the University of Belize. In the following presentation, we will be dealing with capacitors and resistors in parallel and series circuits. In various circuits, as you would have known, there are capacitors and resistors. Some of the questions you might have is, what are these and what are their purposes? These questions will be answered in the following slides. We will also deal with how to find the total capacitance in a series circuit and in a parallel circuit, and how to find the total resistance in both series and parallel circuits. Using the information given and worked out, we will find the voltage in the circuit. But first we must consider the following. Capacitors are represented by these parallel lines with the connected lines to it. And resistors are represented by the following image, as you can see here. The power source will be represented as the following: a long line and beside it a small, shorter line. The long line is always positive and the short line is always negative. Now for capacitors. Capacitors basically consist of two plates. One plate being positively charged and one plate being negatively charged. As can be seen here, this plate is positively charged while this plate is negatively charged. Each capacitor has a capacitance, and the capacitance of a capacitor can be measured in farads. Now, given the following diagram, as you can see here, we have our power source down here, with the long line being the positively charged and the short one negatively charged. And up here, we have our capacitor. Given the diagram above, we can find the following truths. The charge of the system is equal to the capacitance times the voltage, and therefore the voltage equals to the charge of the system divided by the capacitance. Now for capacitors in series. Here we have a series circuit with two capacitors. We can say that the total voltage equals to the summation of the individual voltages, which is V1 and V2, seen here and here for each capacitance, which capacitor C1 and C2. Since we know already that the charge equals to the capacitance times the voltage, therefore we can say that the charge also equals to the capacitance times the first voltage, the first capacitance times the first voltage, and for the second capacitor, the charge equals to the second capacitance times the second voltage. And since we have said before that the total voltage equals the summation of the individual voltages, we can say that the first voltage equals to the charge divided by the first capacitance, and the second voltage equals the charge divided by the second capacitance. Because the charge for the first capacitor equals to the first capacitance times the first voltage, and the charge for the second capacitor equals to the second capacitance multiplied by the second voltage. Since we already know that the charge equals to the total capacitance times the voltage, therefore the voltage equals to the charge divided by the total capacitance. And since also, as we have said up here, the total voltage equals to the summation of the individual voltages, we can then say that the charge divided by the total capacitance equals the charge divided by the first capacitance plus the charge divided by the second capacitance, as seen here. And if you will divide both sides of the function by q, which will be, if we would divide this function here by q, we would get 1 over c equals 1 over c1 plus 1 over c2, which is 1 over the total capacitance equals 1 over the first capacitance plus 1 over the second capacitance. Therefore, a general function would be, for capacitors in series, the total capacitance is the reciprocal of 1 over the first capacitance plus 1 over the second capacitance until we have all the capacitance covered. Or it will be the reciprocal of the following, of the function shown. Now, for capacitors in parallel, consider this. As said before, the charge equals to the sum of the individual charges. And since we know that the total charge equals the total capacitance times the voltage, we can see that the charge equals to the summation of the individual charges, and then if the charge equals to the total capacitance times the voltage, therefore the total capacitance times the voltage equals the first capacitance times the voltage plus the second capacitance times the voltage. I will restate that. The total capacitance times the voltage equals to the first capacitance times the voltage plus the second capacitance times the voltage. And if we would divide all sides of the equation by V, we would get that the total capacitance is the summation of all the capacitance present. Or as seen here, the total capacitance equals C1, or capacitance 1 plus capacitance 2. Therefore, for capacitors in parallel, we get the total capacitance equals the summation of all the capacitance present in the system. Now, in reviewing capacitors, we see that for capacitors in series, the total capacitance is the reciprocal of 1 over the first capacitant plus 1 over the second capacitant plus 1 over the third capacitant for all until you have covered all the capacitances in the system. While for capacitors in parallel, the total capacitance is the sum of all the capacitance in the system. Now for resistors. Each resistor has a resistance which is measured in ohms, and here this is the symbol for ohms. Now if we would see the following diagram, here having our power source, this side being positive and the side being negative, and here we have our resistor. We can say that the voltage in this system here equals the current, which is I times R, or V equals I times R. As said before, I is the current that flows through the circuit and it is measured in amps. V is the voltage and it is measured in volts. And R is the resistance or ohms in the resistor. Now for resistance in series, if we would analyze this here system, we will see that we have two resistors that are in series. Each one has its own resistance, resistance 1 and resistance 2, and its own voltage. Since the voltage equals V1 plus V2, or the sum of all the voltages present, and also voltage equals the resistance times the current, we can say that the current times the total resistance equals the current times the first resistance plus the current times the second resistance. And if we would divide all sides by I, our function here, I times the total resistance equals I times the first resistance plus I times the second resistance. If we would divide that by I, we would get that R, which is the resistance total, equals R1, which is the first resistance, plus R2, which is the second resistance. Or we could say that the total resistance equals to the sum of the individual resistance present. Therefore, for resistance in series, the general function would be the total resistance equals to the sum of all the present resistances. Now for resistance in parallel. If we would note the following diagram, we see here we have three individual resistors, each with their own resistance and each with their own current. Note that the total current equals to the sum of all the individual currents. And given this diagram, as said before, the total current equals to the sum of individual currents. Since the voltage equals to the current times the resistance, it can be said that the current equals to the voltage divided by the resistance. And as we said, the total current equals to the summation of all the individual currents in the system. And we could write all of this as the voltage divided by the total resistance equals to the voltage divided by the first resistance plus the voltage divided by the second resistance plus the voltage divided by the third resistance. And if we would divide all sides of that equation by V, we would get that 1 over the total resistance equals 1 divided by the first resistance plus 1 divided by the second resistance plus 1 divided by the third resistance. Hence, for resistors in parallel, the total resistance is the reciprocal of 1 divided by the first resistance plus 1 divided by the second resistance plus 1 divided by the third resistance for all the resistances present in the system. Now we shall review what we have learned in resistors. For total resistance in series circuits, we see that the total resistance equals to the sum of all the present resistances in the system. While for total resistance in parallel circuits, the total resistance is the reciprocal of 1 divided by the first resistance plus 1 divided by the second resistance, and that continues to all the resistances in the system. Now we shall see the similarities in resistance and capacitance in capacitors and resistors. Here, for capacitance in series circuits, the total capacitance is the reciprocal of 1 divided by the first capacitance plus 1 divided by the second capacitance, and this continues throughout all the capacitances in the system. Now for resistance in parallel circuits, we note that the total resistance equals the reciprocal of 1 divided by the first resistance plus 1 divided by the second resistance plus 1 divided by the third resistance for all resistance in that system. It continues to all resistance in that system. Now we must note that this here formula for total capacitance only occurs for series circuits, while this formula for total resistance only occurs in parallel circuits. Now for capacitance in series circuits. The total capacitance equals the sum of all the capacitance present in that system. While for resistance in series circuits, the total resistance equals the sum of all the resistance present in that system. Note that this equation only works for total capacitance in parallel circuits, and this equation for total resistance only works when resistors are in series circuits. Any questions?